Internal combustion engines do not produce the maximum amount of power they are capable of due to the lack of air available at higher RPMs. Back in 1905, over 115 years ago, Swiss engineer Dr. Alfred Buhe came up with the design for a piece of technology known as the turbocharger. The whole premise of the turbocharger is to increase the volumetric efficiency of the engine by forcefully inducing air into the combustion chamber of the engine during higher RPMs. A vehicle equipped with a turbocharger allows the engine to run more efficient, more powerful, as well as maximize its full potential. Turbochargers increase engine power by rapidly compressing the intake air before it enters a combustion chamber of the engine. The turbine is operated by rapidly expanding exhaust gases. The heat and pressure of the exhaust gases act on the turbine wheel, spinning at upwards of 200,000 RPMs. This power is transferred through the shaft and directly into the compressor wheel. Because the fins of the compressor wheel are opposite to the turbine wheel, this sucks and compresses, forcing a vast quantity of air into the combustion chamber of the engine. Due to how the turbine is driven, the added power is a result from exhaust gas scavenging. This is essentially free work produced by the engine, as the exhaust gases would normally just be forced out the tailpipe anyways. As long as the engine is designed to handle the extra stress caused by the increase in compression, the turbocharger will successfully increase the overall power the engine makes. Turbocharger applications include a few components to make sure it operates as efficiently as possible. These include center housing and rotating assembly, turbine wheel, shaft, compressor wheel, intercooler, and the wastegate valve. The center housing and rotating assembly, or CHRA, houses the shaft, shaft bearings, turbine seal assembly, and compressor seal assembly. Each wheel has its own spiral-shaped enclosure, which looks like a snail shell. This is designed to redirect the exhaust and intake airflow. This component is also connected to a line which shares oil from the engine. This is necessary to keep the shaft and bearings, which are spinning upwards of 200,000 RPMs, lubricated. The turbine wheel, or hot wheel. The forces of the exhaust gases act on the turbine wheel, spinning at very high RPMs. This scavenges waste gases and turns it into usable power. The fins are angled to direct the air into the center of the housing. This creates an airflow called a vortex. Because the turbine is designed to run very hot, upwards of 950 degrees Celsius, it is made from a very heat-resistant cast iron. The shaft. This connects the turbine wheel to the compressor wheel, transferring all rotational energy of the turbine to the compressor wheel. This requires lubrication as most of the frictional operation forces are acting on it. The compressor wheel, or cold wheel. Made with the same fin design as the turbine, only reversed. The compressor wheel spins with the turbine wheel through the connection of the shaft. The fresh air flowing into the compressor from the intake is then caught by the spinning blades. The air is then thrown outwards by centrifugal force, which gets directed into the intercooler. This generally begins to compress air at around 2,000 RPMs. The intercooler. This is a separate radiator designed to remove the heat from the pressurized air before it enters the intake manifold of the engine. By doing so, the air going in is cooler, and as air gets cooler, it becomes more dense. With denser air, this improves efficiency, which in turn improves horsepower, fuel economy, and torque. The wastegate valve. If pressure from the turbocharger becomes too high, this can cause knocking in the engine. Because of this, the engine output can decrease. It is also possible for the engine to self-destruct from too much pressure. That's where the wastegate valve comes in. It helps regulate the pressure in the turbine housing so that a certain amount of exhaust gases can bypass the turbine when the boost pressure exceeds a determined value. The wastegate operation can be determined either by manifold pressure or electronically from the PCM. Airflow. The airflow of a turbocharged system is a bit different than your typical naturally aspirated engine. The air starts by being pulled through the air filter by the compressor wheel, which forces it through the intercooler. From the intercooler, the air is colder and denser, ready to be used for combustion. The air goes straight into the intake manifold and then into the combustion chamber. After being burned, the exhaust air is expelled out the exhaust manifold. There are two paths for the gases to flow, either into the turbine wheel to drive the compressor wheel, or out the wastegate valve if the exhaust pressure is too great. The gases then flow through the downpipe into the exhaust system and are expelled into the atmosphere. Why use turbochargers? Turbocharging offers manufacturers a less expensive way to increase the volumetric efficiency of their engines without having to drastically redesign their engines. As emission standards become more and more strict, it is difficult to design an engine that will not only have increased performance and fuel economy, but also meet emission regulations. This has helped the industry produce high-performance applications in a small, affordable package. Turbocharging also helps to reduce the size of engines while keeping the same performance but better fuel economy and less emissions.